Last time we introduced Boolean algebras, and we gave the five pairs of axioms that are assumed to be true. Today, what we're going to do is use those axioms to prove some theorems. And these are important theorems, so your author calls them laws. Now, for each step in my proof, I'm going to use something I already know to be true. Either one of these axioms or a law that I've already proven. All right, so for shorthand, I call the associative axioms, either one, that pair, AA. I call the commutative axioms CA. Get it? The distributive axioms DA, the identity axioms IA, and the complement axioms I'm going to have to call Comp A because I already have a CA. So when I use them in a proof, what I mean is I'm using either this statement or that statement, but that'll give you the reason that I'm able to go from one step to another. All right? So that's the way I'm going to do. Beside each line, I'm going to put why it's true. So let's go to our first set of laws, which are called the idempotent laws. Idempotent laws, okay? So, which I'm going to abbreviate IL if ever I need to use them again. Okay, now the idempotent laws, remember I said Boolean algebras aren't exactly like college algebra kinds of things, so these results, in fact, you won't find true in algebra, but they're true in a Boolean algebra. Okay, so I have two idempotent laws. One is if I have anything in S and I add it to itself, I get the same thing back. That's not true in algebra, seldom. All right, so x plus x is always x. And by the way, the dual statement, since axioms come in duals, so do all their theorems, right? The dual statement is what? I replace the plus with a dot. X dot x is always x, right? So those two things are true in a Boolean algebra, but I have to prove them. How do I go about proving them? I have to use these axioms because that's all I know. Okay, so here we go. I'm going to start on one side of this equation, and I'm going to get to the other side. So I'm going to start with x. Now I'm going to write x as a clever way, x plus 0. By what? The identity axioms. All right, so I go to the identity axioms and it says, what? Anything add 0 is that thing back. So that's the one I'm using. Okay, so x is just x plus 0. Now I'm going to write 0 in a special way. X complement. Okay? How do I know that 0? By the complement axiom, which I happen to have right up here. Yes? X complement x is 0. By the way, by commutativity, x complement x is the same as x complement, right? There is no difference. All right, so I write 0 as that. And then what am I going to use? I'm going to use that funky little distributive axiom. Which one am I going to use? The one that's not true in general. If you look at distributive axioms, they either allow you to go from this to this or backwards from that to that. Right? So I'm going to use x plus two things dotted is x plus the first dot x plus the second. So let's go down here. See, so I have x plus and then two things dotted. So the second distributive axiom says it is what? x plus the first, x plus x, dot x plus x prime. Okay? Now, that's the distributive axiom. Now, what's x plus x prime? Well, by the complement axiom, the first one, x plus x prime, which is the same as x prime plus x, again, because of the commutative axiom, is just 1. So this is just 1. So I replace it by 1. And now 1 dot anything is that thing back. What axiom am I using there? The identity axiom. Anything dot 1 is that thing back. Okay, so that's the identity axiom, and all of a sudden I started with this side and I ended with that side. So I'm done. All right, now how do I prove it's dual? Well, the beauty of it is I can actually write out a proof for the dual by taking each statement here and just changing it over to the dual. So if I take the statement x equals x plus 0 and I write the dual, remember, switching plus to dot, 0 to 1, what do I get? X equals x dot 1. By the way, that is true by the other identity axiom. Not this one, but the other one. Okay, so again, I'm going to start this side, end up with this side. And the argument really is I just take each one of these statements over here and I write its dual. Now, the interesting thing is my reasons for why it's true don't change. As in, it's still one of those pairs. It's just the other pair. Okay, so I could either dualize this argument and I get this, or I could just go and do it again, right? So then x plus x prime, I know that's 1 by the complement axiom. And then by the distributive axiom, x dot this plus that is x dot x plus x dot x complement. But the complement axiom tells me x dot x complement is 0. And then if I take 0 and add anything, I get that thing back. So going from here to here is using one of the identity axioms. And there you have it. I started with one side, I end with the other. The reason why I'm showing you these arguments is both to develop these laws and also to show you how one argues things in a Boolean algebra. All right? So there are my idempotent laws. If ever I have to use them, I can, because I've already proven them. And I abbreviate them IL. Get it? Idempotent laws. All right. The next pair of laws or theorems that I'm going to prove are called bound laws. Right? Which I abbreviate BL. They are, the first one is x plus 1 is always 1. Now that's something that's not true in algebra, in college algebra, but it is true in a Boolean algebra. In some sense, if I take 1 and add anything, I get 1 back. Now what's the dual of that statement? Well, writing the dual, remember, take plus, replace it with dot, take 1, replace it with 0. I get x dot 0 is 0. Right? Now that is true in college algebra. This one is not. In a Boolean algebra, they are both true. All right? So let's see how I would go about proving that. Well, I'm going to start with this side and end up with that. So I start with x plus 1. All right, so x plus 1 is x plus, and now I'm going to write 1 in this clever way. x plus x complement. What is that? That's one of the complement axioms. I'll prove it to you. X plus x complement, or its reverse, is always what? 1. So I'm using comp A. And now what I'm going to do is I'm going to reassociate. I'm going to group these x's together. So I'm using the associative axiom. Now, guess what I'm going to do? I'm going to use this theorem I already proved. X plus x is always x. That's one of my what? Idempotent laws. All right, so now I can use this result since I've proven it. So x plus x is just x. And then x plus x prime, that's just 1 by the complement axiom. You should note that had I not proven the idempotent laws first, I could not use it here. Right? So the order I proved these was important. I needed the idempotent laws to prove the bound laws. Right? All right, now, how do I prove the dual? And the answer is just by taking each one of these statements and translating it as a dual. So I'm going to let you read that argument right there. It's just the dual of this argument. So there are my bound laws.